The purpose of this module is to introduce the while loop. We've already seen how to use a for loop to execute a collection of statements a given number of times. For example, suppose we want to add the integers from 1 to 100. We can proceed as follows. Set s equal to 0, for I equals 1 to 100. Add I to s, so s equals s plus I. The sum of the integers from 1 to 100 is 5050. But now suppose we want to repeat a collection of commands, but we don't know how many times. At least we don't know before we start. For example, suppose we want to add the integers 1, 2, 3, and so forth until the sum is at least 100. We can do this using a while loop. So let me set my sum to 0 again. Let me also set my integer I to 0. Now I want a loop that will execute as long as the sum is less than 100. And as long as that's true, I'm going to add 1 to I. I'm going to add I to s. And that's all. Now the sum is 105, which is more than 100. And it took 14 integers to do that. In other words, I had to add the integers 1, 2, 3, etc. up through 14 in order to reach a sum that's at least 100. I can check that if I want as follows. The while statement uses a logical condition to decide whether to stop or to keep going. A logical condition is actually any expression that evaluates to a numeric value. 0 is interpreted as false and any non-zero value is true. Usually we use logical operators as opposed to arithmetic operators to form logical expressions. Here are some examples. I can ask if 1 is less than 2. The answer is true, non-zero. I could ask if 1 is less than 0. The answer is false, in other words, 0. Now usually our logical expressions will involve variables, so let me set x equal to 3. And then I could ask, is x greater than 0 and x less than 5? The answer is true, it is. I could ask, is x greater than 0 and x less than 3? The answer is false because x is not less than 3. I could ask, is x greater than 0 or x less than 2? That's true. X is greater than 0 even though x is not less than 2. So that or statement is true. I could ask, is x greater than 5 or x less than negative 5? And the answer is no. Neither is true. I could ask if x is equal to 3. Now notice the logical equals operator is a double equal sign. We obviously can't use x equals 3 as the logical condition because x equals 3 is an assignment statement. Is x equal to 3? Yes. Is x not equal to 3? The answer is no. X is 3, so it's not the case that x is not equal to 3. I can form more complicated logical expressions. So let me define a couple more variables. I could ask if it's the case that x is greater than 0 and y is greater than 0 and z is greater than 0. False, because z is not greater than 0. Not all three of those are true. I could ask if x is negative or y is greater than 0 and z is greater than 0. That is also false. X is not less than 0, and it's also not the case that both y is greater than 0 and z is greater than 0 holds. When writing a while loop, it's important to make sure that the condition to terminate the loop will eventually be triggered. Otherwise, the result is what's called an infinite loop, a loop that never terminates. Remember my earlier example of summing the positive integers until the sum is at least 100. Suppose I make the mistake of posing the problem as summing 1, 2, 3, etc. until the sum is exactly 100. In fact, the sum is never exactly 100 because the sum from I equals 1 to 13 of I is 91, and the sum from I equals 1 to 14 of I is 105. So the code that I'm about to write results in an infinite loop. So I set the sum to 0, I set I equal to 0, and then I want to continue as long as the sum is not equal to 100. While that's true, I increment I add I to s, and then I execute the loop. And then I wait, and I wait, and I wait, and eventually I might realize that something is wrong. I can use Control-C to terminate the loop. That'll kill the loop without terminating Matlab. And then let's see. Well, I've already added up more than 1 billion integers. The sum is 7.5 times 10 to the 17th, and that loop would never have ended. In an example like this, I can make sure that the while loop ends by using a more complicated logical condition. Let's start over again and set s equal to 0 and I equal to 0. And now let's sum while s does not equal 100 and I is less than or equal to 100. I know that I don't have to sum past I equals 100. If my sum isn't equal to 100 by then, it certainly never will be. Now the loop terminates. The sum is not exactly 100, and I can see that the loop terminated because I exceeded 100. Now let's use while loops to explore the parameters of the floating point system. First, let's determine the smallest positive floating point number. We've already seen that this number should be 2 to the negative 1074. I'm going to write and execute the following code, and then I'll explain it. The idea is to start at x equals 1 and divide x by 2 until it underflows to 0. I need two variables so that I have a record of what x was just before dividing it by 0 caused the underflow. So you notice after the loop terminates, x1 is 0. That's what it has to be because that's the condition that causes the loop to terminate. On the other hand, x holds the previous value of x1. That is the smallest positive floating point number. It turns out to be about 4.94 times 10 to the negative 324. If I take the log base 2 of that number, I see that it is negative 1074, as expected. Now let's determine the precision of the floating point system, the number of digits in the mantissa, by determining the smallest power of 2 that can be added to 1 to produce a distinct floating point number. Once again, I'll write the code and then I'll explain it. What we see is that 1 plus 2 to the negative 53 is equal to 1 in floating point. Now 54 binary digits are required to represent 1 plus 2 to the negative 53 exactly. So this shows that the floating point system has fewer than 54 digits in the mantissa. On the other hand, 1 plus 2 to the negative 52 is greater than 1 in floating point. This shows that the system has at least 53 digits. And so we see that the floating point system has exactly 53 digits. But I want to remind you that 1 is a hidden bit. It's not explicitly stored. So IEEE double precision manages to store 53 bits of information in only 52 physical bits. We could also write a while loop to determine the largest possible exponent in the floating point system. I'll leave that as an exercise.